The topic for this week is independence. So we will further go into the notion of independence. It will talk about independence of events, independence of random variables. So before we start the concept of independence, which you have seen before, I just want to remind you about conditional probability definition. Suppose you have a sample space omega, two events A and B, which should be element of the power set of omega. So it could be a sigma field, but let's just assume that to be the omega is the set of all interesting events. If this is the case, then probability of A given B is defined to be probability of A intersection B upon probability of B. So you should think of this as probability of A given that event B has happened. Given this definition, we defined two events A and B, again element of the power set of omega, to be independent if and only if this condition holds true. The probability of both happening is multiplication of probability of A and probability of B. So this we took as the definition of independence. This definition is closely related to a more intuitive definition, which is that probability of A given B is equal to probability of A. So this is more intuitive because this says that knowing that B has happened does not affect the probability of A. We saw that these were almost equivalent except a boundary case, and I will just leave it as an exercise for you to remember or figure out why these are not exactly equivalent but almost equivalent. So this was the definition of independence. A very closely related concept is the negative correlation or positive correlation of the independence. So what we saw in the independence was that if two events do not affect each other, then we believe that probability of A intersection B should be probability of A multiplied by probability of B. The events are said to be negatively correlated if the probability decreases than what is expected. So other way to think of it is, if we know that A has happened, then the chances of B happening decreases. In a very similar way, we can define positive correlation, which is probability of A intersection B greater than B. So these are the formal definitions. Intuitively, negative correlation means given A, probability of B reduces. And the opposite case for the positive correlation. So two events are linked in a positive sense. If they are positively correlated, they are linked in the negative sense. That means occurrence of one affects negatively on the occurrence of second. Then they are negatively correlated. So let's look at some of the examples. We will start with some examples so it is quite clear whether things are independent or not. We toss two coins, and then A is the event. That first coin is heads, B is the event, second coin is, and it's intuitively clear that since the first coin toss has nothing to do with the second coin toss, these two events are independent. You can easily verify it using formula also. We won't go into that. But this could be generalized. If A is an event which only depends on first coin toss, again it is not completely defined, I'm just saying vaguely that A is some event which only depends on first coin toss, and B only depends on the second one, then A and B should be independent. Actually, many a times this is given in the definition of the problem. So when people say that we toss two coins independently, they are basically saying something like this, that the first coin toss does not affect anything in the second coin toss. So this is how it is stated in many problems. This is quite a clear example of how two events can be dependent. We can take second example. Let's say we have a pack of cards and you pick two cards one after another. And the question is, let's say A be the event that first one is an ace, B second one is an ace. Question is, are they independent? Are events A and B independent? So if you remember our previous discussion, it is very important to realize whether the picking is done with replacement or without replacement. With replacement, your guess should be A and B are independent. Without replacement, then A and B are dependent. An intuitive way to see it would be that if we are doing this experiment without replacement, the first pick is an ace. Now the number of aces have reduced to be just 3 in the pack. So in the next iteration, chances of having an ace have, so definitely they are dependent. Again, this was an example where it was kind of clear that the two events were independent. The third example would be any sample space. Suppose A and B are disjoint events. And again, intuitively, once I know that A has happened, then probability of B is 0. So probability of B given A is 0. Knowing A gives me complete control over B, so they cannot be independent. So these two events are dependent. As an exercise, again, there is a special case when two disjoint events are independent. You need to find that special case. This, I leave it as an exercise. Let us take another example. We toss two coins, not stated anything, then we assume that they are unbiased. Let A be the event that first coin is head. B is both outcomes. Now in this case, it is not clear that they are independent because is not entirely dependent on the second toss. So we can't clearly say whether the two events are independent or dependent. In any such case, we use the definition. So probability of A is half. Probability of B again you can calculate is half. And probability of A intersection B means the coin toss was head and head, which happens with 1/4 probability. This implies that probability of A intersection B is PA times PB. So A and B are independent. So this tells us that whenever in doubt, we can use the formula to verify whether two events are independent or not.